Everyone, it's my great pleasure to introduce Apoorva Khare. He already gave a talk last week. So this is a continuation of his talk. So Apoorva Khare from IISc Bangalore will be talking about total positive matrices, frequency functions, and optimizations of Schur polynomials. Over to you, Apoorva.
Thank you. Again for the introduction again. Yeah, so this is the sort of a second part of my talk, but it is not dependent on the talk. So actually for that reason, some slides will be common, and I apologize in advance. So let me start with some common slides. So just to remind you to set some notation and some basics, everything in this talk will be about real matrices. And so a real symmetric matrix is positive definite if and only if any of these three conditions are satisfied. The quadratic form is positive definite. That's the same as saying U transpose AU is strictly positive if U is non-zero vector. If and only if all principal minors are positive, if and only if all eigenvalues are positive. And these matrices show up in all kinds of, like of course applied sciences, because every matrix which is positive semi-definite is a correlation matrix, and vice versa. But also, of course, in pure math, in analysis, they show up in a bunch of places as old as the second derivative test, the Hessian. Correspondingly, a rectangular, possibly rectangular matrix is totally positive if all minors are positive. So you take any k rows and any possibly other k columns and take the k by k submatrix, look at the determinant. If this is strictly positive for all choices of rows and columns, then this is a totally positive matrix. And so, for example, all entries are positive because they are 1 by 1 submatrices, all 2 by 2 minors are positive, and so on. And so these matrices actually occur all over mathematics, and here are some areas and some names in which of people who have contributed, from analysis in differential equations to, so this is Schoenberg's work in 1930, which predates by 20 years his work on Polya frequency functions in 1951. Probability and statistics, so Sam Carlin is a big name here. He proved a lot of results, including on renewal theory. Schoenberg, of course, established the theory of splines, starting from Polya frequency functions. Recently, Groshnik, Stockler, and Romero have worked on Gabor analysis using Polya frequency functions. Again, very classically, Gantmacher and Krein. And of course, these are matrices, so many people in matrix theory. And then totally positive matrices are sort of type A, and Lustig brought over this idea to other reductive groups in other types. Postnikov worked on the totally positive Grassmannian. There's cluster algebras, integrable systems, of course. Fomin and Zelevinsky also have this famous paper on tests and parameterizations of total positivity. And there is combinatorics. And so then there are several. Of course, this omits a lot of people who have worked on this, on totally positive matrices and functions and kernels. But yeah, so the idea is just to tell you that this is an extremely popular theme in mathematics all over the place. Okay, so a quick recap. If you weren't here last time, then I'll just remind you of this one slide. I won't prove it. So suppose, so totally positive matrices have lots of nice properties, including properties similar to positive semi-definite matrices. So if A is a real symmetric matrix, then A is positive definite, like all the principal minors are positive, if and only if all the eigenvalues are positive. And obvious that a principal submatrix of a principal submatrix is a principal submatrix. So all eigenvalues of all principal submatrices are positive is also equivalent. And the reason why I include this clause extra is because for total positivity, you need it. So this is a result from 1937. Suppose A is a real square matrix. Let me put square for, then all the minors are positive, not just principal. That's the same as saying A is totally positive, if and only if all eigenvalues of all square submatrices are positive. And here again, I don't use the word principal. Okay? And the proof uses two very classical results, and I sort of said it last time, so I won't repeat it here. Okay, examples. Again, some things are common, but the next slide won't be common. So these are sort of important examples. So I want to tell you again, remind you. So the upper triangular matrix where you keep, or maybe this is lower triangular, I always confused. Actually, maybe this is lower triangular. Anyway, so you keep ones on the diagonal, ones below the diagonal, and zeros above, and that's totally non-negative. So take any minors and those are non-negative. If you look at generalized Vandermonde matrices, these are totally positive, meaning if you take increasing real cases, positive, and any real increasing exponents, then the xj to the yk, that determinant is positive. And I will actually prove for you this result on the next slide. And this applies immediately to prove that the Gaussian kernel is totally positive. So now this is an example of total positive kernels or functions. What is this kernel? It's just e power minus sigma x squared. But sigma is some positive real number. So what does that mean? That means that you take any finitely many real numbers and finitely many real numbers y, and look at the matrix. So this is like drawing the submatrix from the whole function, e to the minus sigma xj minus yk squared. And that's an n by n matrix, and that is totally positive. And I'll very quickly tell the proof. I did it last time, so I won't try to not to repeat. So first of all, you want to prove that any submatrix of this has positive determinant. But every submatrix of such a matrix looks exactly like the same form. So it suffices to show that the determinant is positive for every such matrix. But the matrix itself factorizes as a product of a diagonal matrix, e raised to minus sigma xj squared, times the cross term, e raised to plus 2 sigma xj yk, and that is actually a generalized Vandermonde matrix, times e raised to minus sigma yk squared. And now the two outer matrices are diagonal with positive entries, so they have positive determinants, and the middle guy, by property 2, has the same property. Right? So that's right. Anyway, so the real question is why a generalized Vandermonde matrix is totally positive, and that depends on. So that's yeah.
I mean, can we take p between 1 and 2?
What's p?
I mean, in place of 2, the exponent 2. Gxy, when you define g square bracket x.
This exponent here.
Right.
I don't know. So now you're thinking about some kind of a Banach space related property.
Yeah, I mean, that prejudice comes in, right?
Right. Yeah, I mean, first of all, the decomposition doesn't really hold in that case. So it's not immediate whether this is true or false. Okay. I will have to think about it and get back to you, but probably this can be answered using Polya frequency functions, is my guess, in the theory of that. So you have to look at the Laplace transform of e raised to minus sigma x to the p and figure out if the reciprocal of that is in the Laguerre-Polya class or not. That's really the answer. That's if and only if.
Why I'm saying is because exponential minus norm x p for p between 1 and 2 is positive definite.
It's positive definite, is it?
Right.
Interesting. Okay, then that's an interesting question to think about. Okay, I will think about it as well. Thanks. Yeah, but anyway, I'll tell you the result. Well, I mentioned the result last time about take the bilateral Laplace transform and hope that the reciprocal of that is in the Laguerre-Polya class. Then this is indeed a totally positive function, and or at least a totally non-negative function. And if not, then it isn't. Okay, so let me prove for you then that the generalized Vandermonde matrices are totally positive. I'm just reminding you of the statement that you take this matrix and you want to prove the determinant is strictly positive. Well, the first step is to prove it's always non-zero. And that is done in a slightly roundabout way. So you interpret this, so you want to claim this matrix is non-singular, and we will convert the matrix. So you want to prove the matrix times a non-zero vector is non-zero. And we will convert it to looking at fixing the vector itself and changing the x's rather than fixing the xj's and yk's and looking at c. So fix a non-zero vector c with s minus denoting the number of sign changes. So that means you look at the coordinates in the tuple, remove the 0 coordinates, and look at the number of times the sign flips. This is clearly at most n minus 1. Traditionally, or maybe 100 years back, these sign changes were called variations. So I remind you of that. So now define this function. So having fixed the vector c, let x vary across the xj's and more generally across positive real numbers, and look at this function here. Okay. Now Descartes' rule of signs, there is this classical result from 1637, says that this function has at most the number of sign changes many positive roots x. Okay. So in particular, this function cannot vanish at the n values xj because they are distinct and positive. That means there is at least one xj for which this is non-zero, provided the tuple C is not identically 0. And that means that this, but if you look at the value here, this sum here, that is one of the coordinates of this vector here. The matrix times the vector C. And so it just means that this vector, this matrix times the vector is never 0 if C is non-zero. So the matrix is non-singular. And this is called Descartes' rule of signs, but you might have seen this being called Laguerre's rule of signs. So Laguerre in 1883 proved this same result using Rolle's theorem, and that is kind of the modern proof that we all see in papers. The standard proof, if you see in textbooks and papers, is the one with Laguerre's theorem. But this idea of using Rolle's theorem to prove something like this actually predates Laguerre, I believe, and goes back to at least to Poulin in this result called the Hermite-Poulin theorem about real-rootedness of polynomials. Poulin used exactly Rolle's theorem in a similar kind of way. Anyway, so I may call it the Laguerre-Poulin-Rolle trick or something, right? But the idea is to use Rolle's theorem. But so and there's a reason why I'm telling you about Descartes' rule of signs that will show up later in the talk. So what we have shown so far is that the determinant here is always non-zero. Now, how do you prove it's actually positive? Well, the idea is just take a linear homotopy from the powers yk, these general increasing tuple of powers, to the usual tuple, 0, 1 through n minus 1. But then this linear homotopy, a line segment, a parameterized line, if you will, traveling at unit speed or whatever, takes this matrix to the usual Vandermonde matrix. And for the usual Vandermonde, we know the determinant is positive. At every point along that line, the powers keep strictly increasing. So if it's positive and never changes sign at one point, then it has the same property throughout the line, in particular at the initial point. And that's the proof. So that's how you prove, and this is the original proof, I believe, by Gartmacher and Krein in 1937. Okay, so the above notion of matrices then can be generalized to kernels, as we already saw in the Gaussian case. So a function from R to R is a Polya frequency function. If it has three properties, it's integrable. It is not pathological, so it is non-zero at least at 2 points. And then one can prove that if it's non-zero at 2 points, it is non-zero everywhere in between and strictly positive. So it's actually positive on an interval. And it is totally non-negative, meaning what we saw for the Gaussian, which is that you have n increasing x's, n increasing y's, you form the n by n matrix, lambda of xj minus yk, and that has non-negative determinant for every value of n. And therefore, it's just the same as saying that each of these matrices is totally non-negative. Sorry, I should again point out, please feel free to interrupt and ask questions. Yeah. So this is a Polya frequency function, and they have a beautiful structure theory, which I won't get into this time. I sort of talked about it last time. And that was developed by Schoenberg and others. And here is one interesting result that they connect to. And this is a result that appears in a preprint by Karl-Heinz Groschnig in, I think, last month or in July. And it says the following, that psi be the Riemann psi function if this inverse Laplace transform, the Mellin transform, if you will, of this function is a Polya frequency function, then the Riemann hypothesis is true. And vice versa. This is if and only if the Riemann hypothesis. So it's not, it's as hard or as easy as the Riemann hypothesis. The point is, as Groschnig himself remarks, this observation could actually have been made, and maybe morally should have been made, in 1951, when Schoenberg proved his characterizations of Polya frequency functions, because Polya at least had made the observation about the psi function the big capital psi function belonging to the Laguerre Polya class. But anyway, so that observation is now made, and it seems to have been not recorded until 2020, which is remarkable. But yeah, so these functions connect to all kinds of things, as I already told you. Some of those areas are mentioned here, and also to number theory. Okay, I will not go into the structural properties today, but I will tell you a couple of related properties that Polya frequency functions and Tn matrices satisfy. So Schoenberg proved all of these. The first one was for matrices in 1930. If a matrix is totally non-negative, then it diminishes the number of sign changes. So this was what, as I said, it's called variations. Well, the number of variations reduces. So take any vector in Rm, sorry, that's the input vector that has so many sign changes. Apply the matrix, that's the output vector, and that has fewer sign changes. So that's called the variation diminishing property. Variation was just the sign changes. You can do the same. So this is what he proved for matrices. You can do the same thing for functions or for Polya frequency functions. And so the continuous version is that such a function is to be thought of as a kernel, which you integrate against, and the variation denotes the possibly infinite number of sign changes. So of course, so what he's saying is now take any test function, let's say nice enough that it's integrable and so on. Take lambda to be a Polya frequency function, integrate against it to form the output function. Then the output function has fewer sign changes. So it's exactly the same version as the discrete version. Obviously, if this function is badly behaved, and there are infinitely many sign changes, then there is nothing to prove. This has obviously something which is at most infinite. That's just nothing. The real meat of the result is when this has only finitely many sign changes, and then you show that the output function has at most those many sign changes. And that is the tricky version, but that can be deduced from property 1, from theorem part 1. And he does that in his 1951 paper. So this is called the variation diminishing property. Right? Now it is, let's see. And so this is for either finite matrices, as I told you, or for continuous functions, right? For functions on the continuum. But there is an intermediate part, if you will, intermediate variant, which is for sequences, meaning on the discrete set integers. So now instead of having f or lambda from R to R, I would take lambda from Z to R, sorry. So something like this, it's just a sequence. Any function from Z to R is a sequence. And these are called Polya frequency sequences. And that is the focus of the rest of today's talk. So these are just sequences, no integrability, no non-pathological nature, nothing assumed, just the total non-negativity. Right? So such that for any integers or any arguments, L1 to Ln and M1 to Mn, take the determinant of this matrix and that is non-negative. So in other words, this is like a bi-infinite tuplets matrix of this form. And then again, the same idea. You choose so many rows, so many columns, the same number, but in arbitrary positions. Take the determinant that is non-negative. So I'll mention lots of examples after this, or how to create examples even better, after some history. So let me now go back to the history of how these things came up. And these actually predate Schoenberg's 1930 paper for matrices. These actually go back to Laguerre's 1883 paper that I already told you about. So let me tell you why, and first of all, how this total positivity started and how the variation diminishing property. So the property was named by Polya in connection with the number of sign changes. And actually it was in use, the word variation, as I said, at least in Laguerre's paper, maybe even earlier, certainly morally speaking, since Descartes' rule of signs, the variations of a polynomial, let's say, or a vector have been studied. And so here is a sample result that Laguerre proved in that same 1883 paper. Suppose fx is a polynomial. And given gamma, a positive or non-negative real number, look at the power series e to the gamma x times fx. Now, so of course, fx is a polynomial, but e to the gamma x times fx is a power series. It turns out that the number of sign changes of this power series reduces. As gamma goes up, this goes down. Which means the maximum number possible was the one when gamma was 0. But when gamma is 0, this is actually a polynomial. Which means it has only finitely many sign changes. And what we are saying is that the number of sign changes for any positive gamma is less than or equal to that finite number. So that was what Laguerre wrote down in his paper. And you can also show a lower bound, which is the number of positive roots, which is actually Descartes' rule of signs. Descartes' rule of signs says just the gamma equal to 0 result here. But Laguerre says that you can actually refine this for every gamma in between, every gamma positive. So Laguerre did not fully prove this, it seems, and Fekete, in his correspondence with Polya, which was published in 1912, remarks that I can prove this result using the following theorem. And here is his theorem. Take any formal power series with non-negative coefficients. Okay. So with respect to the standard monomial basis, if you try to multiply 1, x, x squared, x cubed, x fourth, and so on, this infinite vector, if you multiply by P of t, then this is the matrix, the linear transformation, the matrix of that transformation with respect to the standard basis. You can just get that very easily. So, for example, multiplying by 1 gives you the first column, C0 plus C1x plus C2x squared, multiplying by x gives you the second column, 0 plus C0x plus C1x squared plus so on and so on. So this is what Fekete claimed. If this matrix, if this infinite array is totally non-negative, then the same variation diminishing property holds for finite x. Finite x means Taylor series of polynomials. There are only finitely many non-zero terms. Notice that this function, the right-hand side, the output vector can be infinite, can have infinitely many non-zero coordinates, but in fact, this is the same result. So this is exactly what you need to prove Laguerre's theorem, provided you can apply it to the matrix coming from the exponential function. So what you want to do is you want to claim that if this is 1, this is gamma over 1 factorial, C2 is gamma squared over 2 factorial, and this is the Taylor series of e to the gamma x, then this matrix is totally non-negative. And that would prove Laguerre's result. So why is that matrix totally non-negative? Or why is the power series of e power gamma x giving you a Polya frequency sequence? And of course, zeros on the other side. So I will actually prove that for you in this talk. So we have gone sort of from Descartes' rule of science to Laguerre's this formulation, which was proved by Fekete, and Polya, who coined the name variation diminishing property. And then we come to Schoenberg, who proved the same property for finite matrices, not for infinite ones, but for the finite matrix case in 1930. Now, from here, you can go in two different directions. You can ask, so the first way you can go is to ask, okay, the variation diminishing property holds for totally non-negative matrices. But then it clearly holds for minus A. And for minus A, the 1 by 1 minors are at least negative. Maybe even the 3 by 3 minors, the 5 by 5 minors, right? All of those are negative or non-positive. So can one characterize all the matrices having the property of the variation diminishing? So that is one way to go. The other is to ask, is there an extra condition such that variation diminishing plus that extra condition implies total non-negativity? And conversely. So can you characterize this property, or can you characterize the Tn matrices using this property and something else? So let me answer both of these questions. Let's start by characterizing the variation diminishing property. So this was actually worked out in the same decade by Motzkin, Theodor Motzkin, in his thesis. So, and the answer is that you have to work with signed regular matrices, and there are some constraints. It's a slightly technical result, but yeah, it's not hard to state. Just to quickly admire Motzkin from afar, just a couple of points about him. So his thesis also contained two fundamental results of linear programming and linear inequalities. One is called now the Motzkin transposition theorem, and one is now called the Fourier-Motzkin elimination algorithm. He also had in his thesis the following fundamental fact in geometric combinatorics, that if you take any convex polyhedron, then that is the Minkowski sum of a compact polytope and a polyhedral cone. And that seems to have been first proved in his thesis. But even beyond his thesis, he branched out into diverse areas and made fundamental contributions in all of these areas. So in combinatorics, he studied the Motzkin number, which is about chords on joining marked points on the circle. He gave the first explicit example of a PID that's not Euclidean domain. He gave an ideal free proof of Hilbert's Nang-Stellensatz with some degree bounds. And he provided the first explicit polynomial. So this is actually Hilbert's 17th problem, that there are polynomials which are positive valued numerically, but not sums of squares, when you have more than one variable. So when you have one variable, then one can prove, Hilbert proved, I think, that if you have a polynomial of one variable, which is non-negative on all of R, then it is a sum of squares of polynomials. But this is not true for two variable polynomials, but it wasn't, an explicit example wasn't known until Motzkin. So this is called the Motzkin polynomial, the Motzkin number, and yeah, he was a remarkable mathematician. Anyway, so that was one way that you can go from this property, which matrices satisfy the variation diminishing property, and that led to signed regular matrices. The other way is to ask, can you add a condition to the variation diminishing property and characterize Tn matrices? And that is also known. And those are characterized by two properties. One is what I just told you, and the other is called the sign non-reversal property. So what it says is that if you take any non-zero vector x, there is a coordinate such that xj is non-zero, and ax, the output vector, has the same coordinate as the same sign as the input vector's coordinate. Right? This is called a sign non-reversal property. Of course, for this, you would want to have square matrices A, because the J and the J must be the same. So this is sign non-reversal for J. So this was known remarkably somehow. So just like you don't need the second property for characterizing sign regular matrices. It turns out that for totally non-negative and totally positive matrices, you don't actually need the first property. You just need the second one. And surprisingly to us, this was actually not put down in the literature. And so in a recent preprint, I think last month, me and two of my co-authors, one of them is my postdoc, Projesh here, and his co-author and I, we proved this result. Given any rectangular matrix, the following are equivalent. The matrix is TPK, meaning all 1 by 1, 2 by 2, ... k by k minors are positive. If you take k to be the minimum of m and n, then you can just say it's TP. So this is a more general result than just total positivity. It's total positivity refined up to a certain order. This happens if and only if every square submatrix of size less equals k has this sign non-reversal property. And you see there is no mention made of variation diminishing. And then one can do the same for Tn, and then it is even more interesting. So it's Tnk if and only if every square submatrix of that size less equals k has the non-strict sign non-reversal property. Non-strict just means you put a bigger equals here, but I still require a component to be non-zero. It's bigger equals here. But I don't even need to verify this for all vectors. This is for all vectors. I need to verify it for one vector. For every submatrix, exactly one vector. And if the matrix has sign non-reversal according to that, then the matrix is Tnk. So it's a finite set of conditions. And again, nothing to do with variation diminishing. So anyway, this was just as a digression. There are properties that are not yet known even. That was very surprising. We asked a bunch of experts in total positivity, but this seems to have been not recorded. Okay, so getting back now to the main theme of the talk, Polya frequency sequences. So examples, the first example is very simple. Actually, it comes from the second. So take any number q between 0 and 1 and look at just q to the n square. So in both directions, for negative integers and positive integers. It turns out to be not just a totally non-negative sequence, but TP. And that's just because you are really drawing this sequence from a Polya frequency function, which was the Gaussian function. So q would be e raised to minus sigma. And then this is just e raised to minus sigma x squared, or x minus y squared. Right? And more generally, if you have any Polya frequency function, then of course you can draw the same. You can draw from it a Polya frequency sequence. That's just obvious. Then there are these things called one-sided sequences, and this is the one that I'm trying to prove for you. This is that sequence where you have zeros until a point, and then the Taylor coefficients of e raised to x. And more generally, you can put gamma to the 0, gamma to the 1, gamma to the 2, gamma to the 3 in the numerators. Right? And the claim is those are also Polya frequency sequences. So I will prove that for you. The one that I won't prove for you is that the geometric series on one side and zeros on the other is also such a sequence. These are what we call one-sided sequences. So they're 0 on half of the line, half of the integers, and positive on the other half. You can also talk about compact or finite Polya frequency sequences. And here are two examples. So the Polya frequency, the sequence where there is exactly one entry non-zero and everything else is 0. So that's like a Dirac Polya frequency sequence. A0, of course, should be positive or non-negative. And similarly, 2 entries positive and everything else 0. The claim is both of those are PF. PF stands for Polya frequency sequences. And let me actually prove that for you. So the proof is very simple. If you look at the infinite Toeplitz matrix for this guy, that is literally a diagonal of A0 and everything else is 0. So if you draw a submatrix of k rows and k columns, you either get a 0 row or a 0 column, or you get the identity matrix times the number A0. You get a diagonal matrix. So the determinant is positive or a 0. And similarly, if you have these two, then you have a subdiagonal, you have 2 consecutive diagonals which have positive entries. Again, in that case, you get either a 0, you get a 0 row or a 0 column when you draw some submatrix from that infinite Toeplitz matrix, or you get a diagonal matrix with A0 on the diagonal and A1 on the subdiagonal, or A1 on the diagonal and A0 on the super diagonal. Either way, you get a positive determinant. So that's why these are Polya frequency sequences. Now from these two, just these two building blocks, these are like my atoms, I'm going to build more and more fancy PF sequences. So first of all, can one classify? So it is natural to understand if one can classify all of them, all the sequences with finitely many non-zero diagonals, and that's what I'm going to give. As I'm going to construct for you all of them, and then the result is that these are all of them. There are no others. So suppose you have, first of all, any one-sided Polya frequency sequence. Let me define for you its generating function. Generating function is the usual thing you do. So if A and B are one-sided sequences, then these Toeplitz matrices are totally non-negative. That's literally the definition. Then you can invoke the Cauchy-Binet formula and check. It's very easy to check that if you just literally multiply the two matrices, infinite matrices, then that is also Toeplitz. And you can check that it is also corresponding to a Polya frequency sequence because of the Cauchy-Binet formula. Therefore, but now what does this product matrix correspond to? It corresponds precisely, the coefficients, the Toeplitz coefficients precisely correspond to the coefficients of this power series. And therefore, if you know two power, so the set of generating functions of Polya frequency sequences are closed under multiplication. That's what the Cauchy-Binet formula is really telling. So now, given the two atoms that I said on the previous slide, I will give you some more examples. So we saw this one is fine. This corresponds to A0 plus A1x. And the constant, if this was 0 and I just had A0, that would correspond to A0. So by the previous slides, A0 times, I can put 1 here and I can divide by A0 for the linear polynomials. So A0 times this is a Polya frequency sequence, meaning the coefficients are, right? So that is one example of a finite Polya frequency sequence. Guess what? It is every example of a finite Polya frequency sequence. So every such sequence is of this form. So yeah, this was proved by these two. Eisen and Edray were students of Polya, and Whitney was Schoenberg's student, and they all proved this separately and together in the 1950s. So a bunch of papers in the early 50s. What about infinite now? So these are all the finite sequences that I mentioned. The ones whose generating functions are negative real rooted. What about infinite sequences? Well, there is such a similar representation theorem, again by the same authors. And I should point out, this is exactly at the same time that Schoenberg brought out his fundamental paper on Polya frequency functions. So all of this seems to have taken place in this 5 or 6 year period from 1947, let's say, to 1952. It was a remarkable time for this area. Just everything got proved then. Here is a special case of generating more examples of Polya frequency sequences from old ones. If I have a bunch of sequences and they converge pointwise at each step, then the limit is such a sequence as well. Why? Because you take a matrix, you take the infinite Toeplitz matrix for each an, that is totally non-negative. So you take some finitely many rows, finitely many columns, that's finitely many entries. The determinant is non-negative. Take the limit of this determinant for each n. You get the corresponding determinant for A, and that is totally non-negative. So that's just obvious. But now, if you know this, then I'm going to give you two applications of this one thing and the result of this A0, A1x. First of all, so I take A0 to be 1, I don't care, and I take all the alpha i's to be equal to gamma over n. Then this 1 plus gamma x over n to the n generates a PF sequence from above. So for each n, this happens. Therefore, for the limit, that generates a PF sequence. And that is exactly e power gamma x. And therefore, Laguerre's result, that missing ingredient in Feket's proof, is now proved for you. There's just simple observations like the Cauchy-Binet formula to multiply generating functions and then just take limits of totally non-negative matrices. That gives you the exponential has the Taylor coefficients of that on the one-sided Polya frequency sequence. And that is what Fekete actually used to prove Laguerre's result in 1912. Okay, that's the first example. The second example is the natural way to go about this. I have a partial product like this. If I can keep going for all n, then I get an infinite product, and that must generate a Polya frequency sequence. And that's what this example says. Product 1 plus alpha jx generates PF sequence. Let's say, assuming some nice summability property, right? So alpha j's are, let's say, positive real numbers or non-negative. And so clearly then 1 plus alpha jx in absolute value is less than e power alpha j times mod x, even for x complex. Right? And so if the alpha j's are summable, then the product of e power alpha j mod x is fine. Therefore, this is fine. So that converges and generates such a sequence. Okay, so now as you can see from the title of the slide, I'm switching gears and moving on to algebraic combinatorics, if you will. So if you look at this polynomial in this power series in infinitely many variables, think of this maybe as a formal power series. The constant term is 1, the linear term is summation alpha j, the quadratic is summation alpha j alpha k. So these should remind you of the title of the slide. These are precisely the elementary symmetric polynomials in the roots. Which means what we are really saying is that the fact that this generates a PF sequence is saying that this matrix is totally non-negative, provided you specialize the variables uj's to equal the alpha j's. So we have now moved from polynomials in real numbers to matrices in variables, okay, and onto to symmetric polynomials in variables. And this matrix, this infinite matrix, is totally non-negative when you specialize to numerically positive values. This is called numerical positivity when you specialize to positive values, but in fact more is true. It turns out this matrix itself is positive in the following sense. Every minor, we wanted to say if you substitute alpha j's in every minor, you get a positive number. Well, you actually get a positive monomial even before substituting the alpha j's. So for example, if you look at this minor here, so clearly every minor, every entry here is a sum of monomials, so that's fine. But if you look at this E1, 1, E2, E1, the determinant is E1 square minus E2. And that is just literally twice this number E2. Sorry, that's literally summation alpha j square plus summation alpha j alpha k. Right? You remove one pair of cross terms, not two. So again, it's a sum of monomials. And this is true for every minor. And actually, that is not the best possible version. A stronger version is that all the minors are in fact skew Schur positives, either Schur polynomials or sums of Schur polynomials. And so I need to tell you what is a Schur polynomial and do that. But so this actually is a result that is very classical. It's not something new. So in the sense, this is the first instance, if you will, of numerical positivity when you substitute the alpha j's, upgrading to monomial positivity, upgrading actually to Schur positivity. And this is called the dual Jacobi-Trudi identity. If you replace the EJs, the elementary, by the complete homogeneous symmetric polynomials, then you get the usual Jacobi-Trudi identity. Yeah. So these are all very old results. But anyway, I still now need to define for you Schur polynomials. So here they are. So given this is one definition of a Schur polynomial, I'll tell you the other one in the next slide. So given a decreasing tuple of powers, so to the algebraic combinatorialists here, I'm sorry, this is a slightly unconventional definition. Usually powers increase and so on. But anyway, the Schur polynomial over a field is the unique extension of the following. Take a generalized Vandermonde determinant, but with integer powers, divided by the usual Vandermonde determinant. So since both are alternating functions, and the numerator is divisible by the denominator, and the ratio is a polynomial, but it's also symmetric. So this is called the Schur polynomial. And this is, of course, you need the UJs to be pairwise distinct and so on. Here is an example. If n is 2, there are 2 variables only, then this is the generalized Vandermonde, and divided by the usual Vandermonde, and you see that's just a geometric series. These polynomials are, first of all, symmetric. That's clear. And they form a basis, in fact, of homogeneous symmetric polynomials, and they have representation theoretic meanings. So that's why they are important, they are well studied. And so if you can prove things like Schur positivity, it shows that there is some, maybe a representation underlying that, because it's an actual representation. It's a direct sum of positive combinations of simple modules over SLN, the Lie algebra, or the GLN in this group. Yeah. But here is the more standard definition. So you see here, I could only use the correct number of variables, as many variables as powers. But actually, you can write this down for infinitely many variables, not just finitely many, but infinitely many variables, thereby allowing yourself to specialize to however many you want them to be 0. So they are defined using semi-standard Young tableau. So the idea, I'll tell you the definition via an example. So suppose I take 0, 2, and 4 to be my tuple of powers. Now note that here I will be dividing this determinant where the powers occur by the usual Vandermonde determinant. So really, it's not the powers, these are not the correct powers on the right-hand side. These divided by these are. So what you do is the following. You subtract from these powers the powers of the Vandermonde, which are 0, 1, and 2. So when you subtract from here 0, 1, 2, you get 0, 1, 2. Now, draw Young tableau with 0 rows in the bottom column, 0 cells in the bottom row, 1 cell in the next row, and 2 cells in the top row. Because this minus 0, 1, 2. Yeah. And now my alphabet, let's say, was 3. This n equals 3. I fill in the cells in the following way. With the numbers can only be 1, 2, or 3. Along every row, the number should weakly decrease. It should be non-increasing. Along every column, the numbers should strictly decrease. And so you can check that these 8 possibilities are the only ones. And 3, 3, 2, because 3 must be bigger than 2, 3, 3, 1, and so on. And now the Schur polynomial is easy to trivial to define. You just take u3 times u3 times u2. So u3 square u2 plus u3 square u1 plus u3 u2 square, and so on and so forth. And that's your Schur polynomial. So u3 square u2, u3 u1 square. These two terms are u3, u2, u1. So I put those in with a coefficient 2. And you can check this polynomial factorizes. Anyway, this is a sum of monomials again. So clearly every Schur polynomial, because of this definition, is a sum of monomials, is a positive sum of monomials. It's some work to prove that this definition is equivalent to the other, in particular that this definition gives you a symmetric polynomial. But that can be done using this theory of Lindström-Gessel-Viennot bijections, if you will. And okay, so now here you have so another example of a Schur polynomial, 0, 2, and 3. So again, you subtract 0, 1, and 2. You get 0 cells, 1 cell, and 1 cell. So you just have a column of 2 cells. And entries must strictly decrease. So these are the only 3 possibilities. So here are 2 examples of Schur polynomials. One of them is this polynomial here. The other is this. Clearly, both of them are sums of monomials. So clearly, if you look at them now as functions, just like we were doing in the total non-negative matrices, the 1 plus alpha j times x product. Right? Yeah. So then if you look at both of these as functions and take the values to be positive, then the functions are coordinate-wise increasing in the positive orthant. The interesting thing is that the ratio of these functions also has the same property, is also coordinate-wise increasing. That's the remarkable property. So continuing from the previous slide, if you look at the numerator separately and the denominator separately, then both of them are monomial positive, Schur positive, and hence non-decreasing, but the ratio also is. And that sounds remarkable. This is not divisible by the denominator. There is no reason a priori to believe this. But anyway, this is true, and it is true in complete generality. So let me tell you a result, and a recent result of how numerical positivity upgrades to monomial positivity, upgrades to Schur positivity. And so that's the result I proved with Terence Tao. So for integer tuples of powers, if you look at the ratio of these 2 determinants, of these 2 Schur polynomials, equivalently, you can look at the ratio of those 2 generalized Vandermonde matrices. Then this, when you view it as a function, you fix the powers and view it as a function. This is non-decreasing in each coordinate, provided the mj's are coordinate-wise bigger than the nj's. So here, 0 is bigger than 0, 2 is bigger than 2, and 4 is bigger than 3. So when you have coordinate-wise bigger equals, then this ratio has the same non-decreasing property. And that sounds very strange, but it actually is true. So let me tell you why. I mean, modulo a big hammer from representation theory or Schur positivity. So the claim is that this, when you treat it as a function, is coordinate-wise non-decreasing. And the answer is, to prove this, you use what first-year calculus students know, the quotient rule of differentiation. So high d low minus low d high, or the other way around, I always forget. Anyway, so the denominator of the quotient rule is a square. So if you want to prove that the derivative is non-negative, you can just look at the numerator, and the numerator is this function here. And you see that I want to prove that this number, when you evaluate it at positive real numbers, this is a positive number or a non-negative number. Well, clearly, it's clearly non-negative, but in fact, it's numerically positive because it's monomial positive. As you see, it's a sum of monomials. There are no negative signs. And that was surprising when we looked at, it was certainly surprising to us when we looked at simple examples like this one to try and get a feel for what needs to be proved. And then it turns out it's even more remarkable. Since we differentiate with respect to u3, because it's a symmetric function, you can differentiate in any variable. So if you differentiate with u3, write this down as sum of a polynomial in u3. The coefficients are symmetric functions in U1 and U2. And the claim is then that each pj, each coefficient is actually a Schur positive function. So first of all, this is multiplied by U3, so there is no constant term. The linear term is U3 times U1 plus U2 times 2U1, U2, this number here. But this is actually a sum of, it's a Schur polynomial times 2. The other coefficient is U1 plus U2 square times U3 square. That one, I decompose the cross term in two different ways and keep one cross term like this, keep the other cross term like this. So you see that each of these coefficients, this polynomial is actually a sum of two copies of a Schur polynomial. This polynomial is a sum of two different Schur polynomials. And so actually the quotient rule, the numerator of the quotient rule in the ratio of Schur polynomials is coordinate-wise is a Schur positive function. And the proof for general is similar. So the claim is, as I said, the lemma is that for any tuple of powers, you look at this ratio that is coordinate-wise non-decreasing, but actually a stronger fact holds. It suffices to show that the numerator of the quotient rule is numerically positive. This follows if it was monomial positive, and actually it is in fact Schur positive. But every coefficient is Schur positive, so you are adding up Schur positive things. This is actually, so now for why this is true, I mean, I just told you it is true. Why is it true? Because the big hammer we use is a Schur positivity result by Thomas Lamb, Alex Postnikov, and Pasha Pilyavsky, and this in the American Journal in 2007. And that's a very general result which is used to prove apparently conjectures of Kunkov and other people. But anyway, this does imply our monotonicity lemma as well, or the Schur positivity of the coefficients here. But in turn, their paper emerged out of Marx Kandera's results in the Journal of Algebraic Combinatorics on determinant inequalities for totally non-negative matrices. So we are back again to understanding determinant inequalities for Tn matrices. Actually, in the paper of Tao and me, we actually proved this numerical positivity alone without appealing to this hammer in a different way, essentially in a similar way that Marx Kandera proved some of these inequalities. And also Don St. Richards proved them. So that's a separate numerical positivity proof using total positivity. The other thing to remark, as I mentioned here, is that this function was a ratio of Schur polynomials. And as I said, Schur polynomials are ratios of generalized Vandermonde divided by the usual. So the usual Vandermonde would cancel, and you would just be looking at a ratio of two generalized Vandermonde matrices for integer powers. But if my arguments are, to be the ones which you raise to these integer powers are positive numbers, I don't need to worry about integer powers. I can raise them to real powers. And then the same exact result holds, and that's what we really prove in our paper. Fix for real tuples of this kind. Actually, you don't even need bigger equals 0 here. For real tuples of increasing these and increasing this, this function, where you look at the u raised to the m's and u raised to the n's, the Vandermonde determinants, that ratio is non-decreasing in each coordinate. That's really the more powerful, the more stronger version. So that's one application of totally positive matrices, totally non-negative matrices. As I said, not this Schur positivity proof using the big hammer, but our other proof. But then that other proof also goes through further for real powers, for generalized Vandermonde matrices, which are totally positive. So in particular, what does this lemma imply? It implies the following result. Suppose I take all my coordinates of u's to be bigger than 1. Then because this function is coordinate-wise increasing, the ratio here is bigger than the same ratio evaluated at 1 on 1 on 1. That's just what I just told you we proved on this part of the positive orthogonal. And this is true when m dominates n coordinate-wise. Right? So, but maybe again there are other powers, other tuples of powers, m and n, bold m and bold n, for which the same inequality is true for all u like this. So it's natural to ask for which ones does it hold, and that as an application of the Schur monotonicity and other things, we proved again as Tau that again So now I don't assume that the mj is dominant the nj coordinate-wise. Suppose I have increasing real integer powers. I can also take real powers. Sorry, I don't need to have integer powers here. The above inequality holds for all u in 1 infinity to the n, if and only if m weakly majorizes n. So this seems to be a new characterization of a fundamental type of inequality, weak majorization, using symmetric functions, using Schur polynomials. So there are all kinds of connections in mathematics, and this was fascinating to us. A priori, we would not have thought of, one would not have thought maybe of relating symmetric functions to this, except for the next slide, which I will tell you. But even that was in 2011. So before this decade, certainly people had not really made this connection. Okay, weak majorization means that start from the top limit and take partial sums going down, and each partial sum for the m's beats that for the n's. Okay, that's weak majorization. This problem was originally studied again by Marx Kandera and others in 2011. And that time they wanted to understand for which u does this inequality hold for the entire ortho. So there should be 0 infinity to the n, not 1 infinity to the n. And this is their theorem. If you know that this inequality holds on the positive ortho for integer values, then m must majorize n, not weak, but majorize. Majorize just means it weakly majorizes, but also the total content, the summation of mj's, equals the total content of the nj's. So the last nj really catches up, even though it is less than the other nj's. Okay, so that is the result. They also made a conjecture. They made a conjecture that the converse result also holds. Namely that if you have m to weakly majorize n, then this inequality must hold for every u in the ortho. So remember, we proved the if and only if, and this was a conjecture of Marx Kandera and others. And this was actually proved by Sovritsra in 2016, also in the same journal, in the European journal. And he proved that the conjecture is true. So it's an if and only if here, just as our result was an if and only if. Of course, we derived our result later than theirs. And so once again, these results provide novel characterizations of majorization or of weak majorization through Schur polynomials, or you can even replace them, as I said, by generalized Vandermonde determinants, and through the proof techniques that originate also in total positivity, not just in this. Okay, and maybe I have time to end with a question, if people are interested. And so why did we end up, why did we need that Schur monotonicity lemma, that this ratio of Schur polynomials beats the value at 1 when the u's are bigger than 1, or that this is coordinate-wise, whatever. This concerns something called, something about entry-wise functions acting on matrices, which is what I sort of, a major part of my research is based on, or one big part of it at least. And if you try to maximize this ratio over 0, 1 to the n, then that gives some nice sharp bounds on some kind of polynomial preservers and so on and so forth. And the desirable condition is to maximize this over the positive orthant bounded by a cube. And because Schur polynomials are homogeneous and so on, and these m's always dominate the n's by homogeneity, and it's enough to work on the boundary of that cube. You don't need to work in the interior, just on the boundary of the cube inside the positive orthant. Now, if you want to work with correlation matrices, this was when you work with correlation matrices with positive entries. But if you want to work with all correlation matrices, then you need to bound the exact same ratio over the entire cube now, not just in the positive orthant, but the entire cube. Again, by the homogeneity property, you can forget about the interior and bound it only on the boundary. Now, there is even some constraints on what the denominator must look like. The denominators must be of the power 0, 1 till n minus 2, and then not n minus 1, that's the usual Vandermonde, that would be the trivial polynomial, n minus 1 plus any even number. And there is a different name for such polynomials. They are called the complete symmetric homogeneous polynomials, and they are always positive except at the origin, when the last argument is even. So that's the nice property about these. So here is the question then. Suppose I take any tuple of integer powers where the mj's are increasing and they're bigger equals j for 0, 1 to n minus 2, and mn minus 1 is bigger equals n minus 1 plus an even number. Is it possible to maximize that Schur polynomial divided by the complete symmetric homogeneous polynomial on the boundary of the cube? And if that can be done, that is, as I said, I believe it's not known. And if that can be done, then one would have some kind of a sharp bound for positivity preservers as well. So that's just something to sort of tell you. And finally, the references. So again, pretty much everything I said today is proved or written down to describe to some extent in these lecture notes on my website. And I've tried to mention as many details as possible, as well as details about Polya frequency functions and Schoenberg's results, and this Laguerre-Polya-Schur program, and some connections to Borchea, Brandon, Marcus, Spielmann, Srivastava, and others. Anyway, this is the paper with tau that I was referring to in these last few slides. Is this one? It's under submission forever. The property about sign non-reversal to characterize total positivity is in this recent preprint. It has a nice archive number from July. And then you come to the classical references. So as I said, morally speaking, this whole thing starts from the variation diminishing property, from Descartes' rule, which talks about the variations and bounds on them, to Laguerre, which I did not cite here, to Fekete and Polya. But you see, they talk about on the problem of Laguerre. Well, that was the problem of Laguerre. Now you know which problem. That was the result that they proved for him on Fekete. To Schoenberg in 1930, which I again skipped, to Schoenberg establishing the basic properties of these functions, Polya frequency functions, to his works with Eisen, Edray, and Whitney on Polya frequency sequences, and then the last two are about majorization being characterized through Schur polynomials. Okay, so thank you. That's it.
Thanks, Apoorva. So very nice talk. Any questions?
Couple of elementary stuff. I mean, I'm sorry. Nothing non-trivial about these questions. Maybe, sure. As I said, small queries. Apoorva, are you getting me?
Yeah.
No, for example, Schoenberg's work on positive definite functions, actually, he's motivated by questions about isometric embedding into Hilbert space.
Not really, no. I think they were separate results.
Yeah, but okay, they have been used in a big way to embed certain structures into Hilbert space. Like if I have a finite metric space,
yes,
and I have a certain matrix associated with this, right. Then depending upon the positive definite of this matrix, you can say whether that finite set embeds isometrically into a Hilbert space, right?
That's absolutely right. That's absolutely right. In fact, so that was in 1935 in the Annals, yeah.
Okay, so my question is this. Can we, think of a weaker property on that matrix such that you can embed that finite metric space into a Hilbert space in a weaker way? Let's say in a uniform, as a uniform embedding or as a Lipschitz embedding.
So I mean, there is a old. I don't know actually the answer to that question. I do know this even older result from 1910 of Reche, where it shows that metric space of size n+1 embeds in Rn with the sup norm. So in that sense, it can embed in the Banach space. I don't know what the Hilbert space.
Yeah, but I mean, yeah.
But in
every metric space gets embedded into L infinity space with the sup norm.
Yeah.
But Hilbert space is the main thing.
Right. So I know that probably this was researched extensively by Schoenberg in various ways. Maybe there is something in this paper. There's also a paper he wrote with von Neumann actually on these kind of metric space embeddings. Another paper with completely monotone functions, and maybe one of these papers has something on that along those lines. Yeah, I don't know.
Okay, and something related to this. I mean, that was not the main theme of your talk. This Hilbert 17th problem. I mean, it's revealing. Has it been studied in over more general rings or fields? For example, over Q it doesn't hold certainly.
I think the person to ask these questions would be somebody like I don't know. I think probably Mihai Putinar is one person. Smudgen is one person. And there are one can ask them. I again don't have much information about.
I mean, whether it has been that study has been carried out over more general rings or other domains.
Over other domains for sure. There's something called semi-algebraic sets, like -1, the closed interval. And people have looked at something called the positivity certificate for this, and that's a big area in itself. Something called semi-algebraic geometry. Yeah, and I think Blecherman has some work on this, and maybe even Nemirovsky. I'm not sure. Putinar has some work with some co-authors. So yeah, that definitely has been worked on. As far as more general fields or rings,
Or like finite fields, we don't know.
finite fields. What do you mean by? Oh, just sum of squares. Okay. I would assume that it's yeah. So wait, I'm sure you can every function you can probably yeah. I don't know actually. Yeah. It sounds weird. You should be able to find some. So by the way, Hilbert showed that I think in R2 or maybe in R2 every polynomial which is non-negative on R2 is a sum of 4 squares of polynomials. Sorry, is a rational function, a sum of 4 squares of rational functions.
Okay.
So the Motzkin polynomial, for example, is actually a sum of 4 squares of rational functions, as far as I know. But yeah, there are variants in all kinds of directions, whether on domains, whether in the form of extending the sum of squares, or whether in the fields themselves. And yeah, at least 2 of those I know have been studied. As far as the general fields, I'm not sure.
Thank you.
Any other questions? If not, let's thank Apoorva again for the very nice.
Just 1 minute. I would like to point out that Schur is mostly thought of by people as an algebraist, and his contributions to analysis are given in this article which I wrote in the chat by Dim and Kutz Nelson. It is in 2007, and it is 1868 is the number. I wrote the number. That is one thing. Second thing is that Schur's contribution to projective representations is great.
Yes.
He called them as fractional representations, for which the idea comes from complex analysis, but projective representations are used a lot in analysis and quantum information theory. So I tried to highlight this in my talk several years ago.
Yeah, thank you. No, actually, that's right. I see the contribution here. That's a wonderful expository article and a wonderful survey article. It is almost 100 pages long. Remarkable.
Yes,
And
that's great. Yes.
So,
yes.
my training wasn't representation theory.
But the longest one is that 100 page.
Yeah.
There were 3. Yes.
So I was algebraist because my training wasn't representation theory, and even Schur polynomials and so on. But his tremendous contributions to analysis, to root locations, to multiplier sequences, to projective representations, all over the place. And this contribution actually is a part of this Schur memorial volume, Schur memoriam volume. And it's available online somewhere. So letters, even letters written by Schur to people, by people to Schur, and yeah, it's available. And it's a fascinating historical document, mathematical document, and then there are some recent papers by other people as well, including collaborators or students in that volume.
So it is I Schur or Jai Schur?
Yes. So somehow earlier the articles got published under J Schur, and so the old results are always under J Schur, but it is actually Jai Schur, so it should always be.
Yes. No, I'm calling it in Hindi Jai Schur.
Oh, Jai Schur. Oh, okay. Jai Schur.
Okay. Thank you.
One also knows about some of his works in Banach space theory, I guess.
Is that so? Maybe it's in that article. It's too long. I think.
Yeah. Actually, there is a very important property, so-called Schur property. So that's used in a big way in vector valued integration, taking values in a Banach space.
Yeah.
So such guys are universalists.
Hello. Apoorva, it was a beautiful talk. I would love to see your book on because some of the things they look familiar, although I don't work in this kind of area. But it's a beautiful talk. Let me tell you, and I would love to see your book.
It's so beautiful that I very much have fallen in love with this subject recently. My book is available on my website and it's still undergoing some updating, but it should be mostly done by the end of next month. But as much as is on my website. And
Thank you.
And the parts about Polya frequency, sequence, and functions, that part is basically stable. So I won't be adding to that, the foundation part. But yeah, I'll update it very soon to finish.
Thanks. Bye.
Any further comments or questions?
Is any other talk lined up for this series by Apoorva?
No, I am done.
We would we would love to.
At some point, so I was genuinely thinking of giving a course on Polya frequency functions and this whole thing, developing all of these proofs in detail, except the fact that I still don't know how on-time teaching is going to be. So I'm waiting to find out first of all, how the experience is. I will be start teaching in October, so next week, next Thursday is hello class. The following week we start teaching. Once I understand and if I feel comfortable with that, then next semester I might actually offer such a course, and then I'll certainly get Apoorva. Everybody knows here, Apoorva. But so far, at least, I'm trying to just finish my book. I mean, that's taking longer than I guess it always takes longer than planned.
Well, I had the good luck of attending one of your, one of your seminars on positive definiteness.
I was teaching a course. Yeah, you were in IISc at that time. Some of the other parts of my book.
Right.
Riddhi, you wanted to say something?
Yeah, it was just that tomorrow we have this talk under aegis of Indian Women and Mathematics by Cheryl Prager from Australia, and I'll tell Krishnan to circulate. It's on YouTube as well as on Zoom. It's there on our IWM website. The details. It's at 3:30 in the afternoon India time. And I'll tell Krishnan to circulate. I hope to see many of you there.
What time did you say,
3:30 p.m. 3:30 p.m. And this time we have more seats on Zoom also, 300 participants. And YouTube is also there.
So is there an upper limit on the number of participants?
300, so I don't think we'll reach there. So don't worry about it.
Tomorrow we also have one by Ramurthy at 7:30.
Yeah, I saw that. So please circulate that email to everybody. Because I don't have everybody's email ID. So.
Sure, I'll do that. Thank you.
Thanks. Yeah.
So, Professor Sophie, I just wanted to say that Ramurthy's talk is today at 7:30 p.m.
It's today? I thought
Yes. It is 24th of September.
That's today.
Oh my God! Oh my God! Oh my God! I messed it up. So is it at what time? 7:30, right?
7:30 p.m. Yes.
Oh, I have incorrectly written the date. Oh my God. Okay, thanks for reminding.
You're welcome. Yes.
We meet after 2 weeks, Krishnan, again, Atul?
Yes.
Yes. That's Debashish lined up for us.
Debashish, you're giving a talk?
We will announce it formally. But let's
so what is the title of his talk?
We will announce it. Sorry, I can't recall. Debashish is sitting next to Riddhi probably. We will announce it. Yeah.
He also doesn't remember.
Before that, we should probably thank the speaker of the day.
Yeah.
Atul.
Yeah. Apoorva, thanks a lot.
No, what stands apart in case of Apoorva's presentation is the absolute clarity. So
yes.
Yeah, that really is something amazing.
Maybe it comes from writing a book. I wanted to go into every detail of history as well as mathematics. So I could very fresh in my mind right now. I'm still writing.
Right.
I just finished writing this part of it.